Hello, my name is Colby and I am working with Brian, and our lab is the Angled Projectile Motion Lab. The purpose is to determine the variables that affect a projectile's range. This is a diagram we created, and then also it's determined on the angle, initial speed, mass, and diameter, and our initial trials will neglect air resistance.
Part 1. Variations on the angle. This is the PHET simulation, and we are starting at 5 degrees and increasing at 5 increments to 90 degrees. The initial speed is 20 meters per second, and we will be firing a 5 kilogram pumpkin.
This is our data that we recorded from our PHET program, the ranges corresponding with each angle, and this is the graph that we constructed from the data, and this is the quadratic equation that represents our data.
And now we are going to show the calculations for linearizing the relationship between angle that the projectile is fired at and the distance or range it travels. So first up, we have our range equation here. Range equals the initial velocity squared times sine 2 theta divided by gravity. So first we are going to break this down, simplify it a little bit to get to our linear relationship. Now we have range equals the initial velocity squared divided by gravity times sine 2 theta divided by 1. Now we can again make this a little more simplified, looking more like a linear relationship. And here we have range is our y. Initial velocity squared divided by g, now that would be our m, our slope value, and sine 2 theta would be our x. Now, so when graphing this, you would graph range on the y-axis, sine 2 theta on the x, and the slope of the line would be the initial velocity squared divided by gravity. This is our linearized data. We have our x values as sine 2 theta in degrees, and our y values is range in meters. Here you can see our linear trend line and our linear equation. Now here we have our linear equation that we got from our graph, and so we have y equals 38.183x. 38.183 is our m value, our slope, which is equal to the initial velocity squared divided by gravity. So we are going to use this equation to solve for the initial velocity. So here we brought gravity up, so we have initial velocity squared equals 38.183 meters times 9.81 meters per second squared. Take the square root of each side to isolate the initial velocity, and we have an initial velocity of 19.35 meters per second. And now we are going to calculate the percent error. We have percent error equals the absolute value of the theoretical value minus the experimental divided by theoretical times 100%. Now we launched the pumpkin at 20 meters per second, and we calculated the initial velocity to be 19.35 divided by the theoretical value times 100%. Calculate this out and it yields 3.23% error, which is very low and indicates that the values we calculated are close to their theoretical. Part 2. Variations on the velocity.
For this portion of the experiment, we will be firing the same 5 kilogram pumpkin at an angle of 5 degrees, starting with an initial speed of 5 meters per second, increasing in 5 intervals of 5 to 85. These are the values that we recorded for velocity and then range. The velocity is the x value, and then range is the y value. This is the graph that corresponds with the data, and then this is also the quadratic equation that corresponds with the data as well.
And now we are going to show the linearization of the range equation when considering changes in velocity. So first up we have our range equation here. Range equals the initial velocity squared times sine 2 theta divided by gravity. We're going to manipulate this a little bit to get a linear equation. So here we have range equals the initial velocity squared divided by 1 times sine 2 theta divided by gravity. This allows us to create a linear equation here where y is the range, sine 2 theta divided by gravity is the m, or the slope value, and initial velocity squared is the x. So when graphing this, the y-axis would be range, the x-axis would be initial velocity squared, and the slope of the line would be sine 2 theta divided by gravity. And this is our linearized data. We have velocity squared as our x values and range as our y. Here you can see our graph and our linear equation here, our squared value. And here we have our linear equation, y equals 0.0188x. 0.0188x is our slope, our m value, and is equal to sine 2 theta divided by gravity. So first, to solve for theta, we are going to multiply gravity times this value here to get sine 2 theta equals 0.0188 degrees second squared per meter times 9.81 meters per second squared. Now these units, they're inverse, so they cancel out. So then you're left with sine 2 theta equals 0.184 degrees. So then we inverse sine of each side to get 2 theta equals 10.63 degrees. Divide each side by 2, and you get theta equals 5.31 degrees. And lastly, we are going to calculate the percent error present in our calculations. Percent error is equal to the absolute value of the theoretical value minus experimental divided by theoretical times 100%. So we launched the pumpkin at 5 degrees each time. We calculated the angle to be 5.31 degrees, which is pretty close. And then we divided by the theoretical, multiply by 100%. We calculated the percent error to be about 6.2% error, and this is relatively close. Part 3. The effect of variations on mass and air resistance on projectile trajectory.
Next, we are going to show that the mass of an object does not affect its trajectory when air resistance is not taken into consideration. First, we are going to fire a pumpkin with a mass of 5 kilograms. And next, we are going to fire a Buick with a mass of 1,000 kilograms. As you can see, the trajectories are the same. With the introduction of air resistance, you can see that objects do not travel as high when affected by air resistance. So first, we're going to fire the Buick without air resistance. And next, with. Previously, we showed that objects of different masses have the same trajectory when air resistance is not taken into consideration. However, with air resistance, you can see the difference. First, we are going to fire a 100 kilogram pumpkin. And next, we will fire a 1 kilogram pumpkin. You can see the difference between the two trajectories when air resistance is taken into consideration.